So the goal here is to use the bisection method to approximate the solution. And there is a unique solution of this equation, cosine of x equals x, and it is in the interval from 0 to 1. To P3, meaning the third approximation based on the bisection method is how far we're trying to go. We're not trying to say what we want to guarantee the error is less than. I think it is helpful, besides having a table here, to draw a picture. Because the picture, I think, helps you avoid making any mistakes, to some degree at least. I did graph this with my calculator. There it is. That's cosine of x minus x. Again, a solution of this equation, cosine of x equals x, is equivalent to a root of this equation, cosine of x minus x equals 0. And this graph that you see here is the graph of cosine of x minus x. Like that. 1 is right about here. 0.5 is right around there. You can see it looks like the root is slightly bigger than 0.7, and indeed it is. But let's go ahead and be careful about the method. So the first step of the bisection method is to take your two endpoints, 0 and 1 of the first interval here. A is 0, B is 1. You would also label this A1 and label this B1. So that's the first step, is do that labeling. And then Pn is the midpoint of those. That's obviously going to be 0.5. It is emphasized in the book that certainly you can find that midpoint by averaging these two numbers, 0 plus 1 over 2. But especially if you're a computer scientist, they talk about how that is less numerically stable than taking the distance between these things, dividing by 2 and adding it to 0. The distance between these is 1. 1 minus 0 is 1. Divide by 2 is a half. 0 plus a half does bring you to a half. Okay, we're not going to really worry too much about the programming, though I will show you a couple of programs today. F of an, that'll be f of 0. Cosine of 0 minus 0 is 1. This value right there is 1. And then f of 1, okay, go ahead and use your calculator. Let's make sure you're in radian mode. We are in radian mode. That's the default assumption with trig functions. Cosine of 1 minus 1. Negative 0.4597. All we're really after is the sign of this product. It's negative. Go ahead and put a minus sign, or you could put a less than 0. But then that begs a question: how do you update the a values? There is an algorithm to it based on the fact that this is negative. It's confusing, though, if you don't look at the picture, right? You know, the new interval's got to be from 0.5 to 1. You know, A2 has got to be 0.5 and B2 has to be 1. In other words, the algorithm says that when this is negative, the next A value equals the previous P value. If this had been positive, the next B value would be the previous P value. Remember that? So we updated A2 equals P1. B2 is equal to B1. But you can see from the picture, it's got to be this interval. You know it's got to be the answer.
Should f of P1 be negative?
F of P1 be negative. Oh, I did the wrong thing, didn't I? Ah, okay. Thank you. Yes, that's going to be positive. F of P1, I was doing the wrong thing there. I did F of B. Cosine of 0.5 minus 0.5, that'll be positive. 0.3776. That product is positive. So that's the condition making A2 equal to P1. Okay, because you can see, again, this has got to be the answer right there. Now, bisect that interval, 0.75. F of A2 is f of 0.5. We've already figured that out. That's the same as the 0.3776. F of P2 is f of 0.75. Cosine of 0.75 minus 0.75. Negative 0.0183. This product now is negative. And so I have to switch it from what I did before. B3 is going to equal P2. 0.75. But again, it's hard to remember that in an algorithm. and I was a little bit too quick when I made the mistake in the first line, the picture is really, really helpful. If you're careful in looking at that graph on your calculator, you know this root right there is a little less than 0.75. It was a little bit bigger than 0.7. So the next interval has got to be from 0.5 to 0.75. A3 has got to be 0.5, and B3 has got to be 0.75, the previous value of P. P3, we'll be able to stop there based on the directions. That'll be halfway between these two things, halfway between 0.5 and 0.75. That'll be 0.625, and that'll be the final answer for P3. If you were interested in going further, you would evaluate first f of A3, f of 0.5, we've already done that. That's still 0.3776. F of P3 would be f of 0.625. So we would do cosine of 0.625 minus 0.625. It's positive, and it's further away from 0 than the previous function value was. Doesn't that seem kind of bad? Shouldn't these numbers be all getting closer to 0? We're trying to estimate the root of this function f of x here. With these p's, these are supposed to be your estimates for the root. Wouldn't we want the one that's closest to 0? What's going on here? This product is positive. So the next time we update the values of A and B, when it's positive, you update the value of A. A is going to be 0.625 and B will stay the same. But doesn't this seem bad? F of P2 is closer to 0 than F of P3 is. What's going on here? Is the bisection method not working? I mean, we could wonder whether F of P4 is going to be closer to 0 or not. Maybe it will be. What am I hinting at here? The bisection method does converge to a root, but it doesn't always get better at every step. And that's a fundamental fact to know about it. Overall, it does converge to the root, but you can have intermediate steps that are better answers than the last step. Let's just go ahead and see what this one ends up being. So average those two numbers now. 0.625 plus 0.75 divided by 2. 0.6875 would be P4. Let's go ahead and evaluate f of P4. Take cosine of the previous answer and subtract the previous answer. That is getting closer to 0 again. But still, P2 evidently is a better approximation for the root than either P3 or P4. Because f of that value is closer to 0. That seems to be the case then, that this would be a better approximation to the root. And indeed, if we were to use technology to find the root more precisely, this number is closer. Go back to your graph. Look for the 0, a left bound, a right bound, and a guess. It's very close to 0.74. In this table, 0.75 certainly is closest. That's P1, this is P2, this is P3, this is P4. Of those, P2 is best. However, if I did keep going, I would eventually get to the point where I'm closer. And all this is guaranteed by something called the bisection method error bound. Bisection method error theorem says this. Suppose you got a continuous function on a closed and bounded interval. It could be continuous over the entire real number line, by the way. I mean, our function here is cosine of x minus x. That is continuous everywhere. But the interval we're concerned about is the interval from 0 to 1. It's continuous on that interval. Again, Our book uses this notation over here. I just want you to feel comfortable with that notation. That's just saying F, when you write this over here, you're saying F is an element of CAB. This represents a set of functions. It's a vector space of functions, in fact. And because of that, it's sometimes called a function space. All functions which are continuous, real valued functions which are continuous on the entire closed interval from A to B. That's all that. It's just shorthand notation for that collection. F is such a function is what this is saying. The C stands for continuous. And we're supposing f of A and f of B have a product that's negative, meaning f of A and f of B have opposite signs. So the graph by the intermediate value theorem has to cross the axis somewhere in between A and B. Is the reason why you focus on that condition. The bisection method generates a sequence. This is just shorthand notation for a sequence, P1, then P2, then P3, then P4, then P5, etc. That's approximating a zero or root P of the function f with this absolute error bound. The absolute error, which by definition is the absolute value of Pn minus P, is always less than or equal to that. B minus A is the length of the entire interval that you started with. And you're dividing that by 2 to the n power, where n is the number of steps you've done of the bisection method. It's very, this is the main theme of this class, to tell you the truth, is error bounds. I mean, yeah, we're going to have lots of different methods that we talk about, lots of different numerical methods for coming up with approximations. But the main theme of this class that makes this a numerical analysis class, as opposed to a numerical methods class, is that we have these error bounds that we want to think about mathematically. For this particular error bound, as far as proving it goes, I'm not going to do the proof. The proof is in the book, but I will draw a picture to make it seem reasonable. But we will be proving some theorems starting on Thursday throughout the semester related to error bounds like this. This is the simplest error bound that we have. This can be used in particular to find a guarantee for the, I should say, minimum number of steps n needed to get within a specified error tolerance. And I didn't mean to cross off the steps n there. My pen did that. Let's see, can I erase it? There we go. Okay, I erased it. Find a guarantee for the minimum number of steps n needed to get within a specified error tolerance. In other words, like if I want to ask myself, how big should n be at a minimum to guarantee that the absolute error is less than 0.01, I could use this inequality. I was thinking of doing this example. We could do it with the example we just did, though. With this example. How many steps of the bisection method would you have to do to guarantee that Pn is within a distance of, say, 0.01 of the true value P? Well, A is 0, B is 1. And that theorem said the absolute value of Pn minus P, which is the distance between Pn and P on a number line, the absolute value of the difference of two numbers always represents the distance between them. Always remember that in this course. I mean, if you had real analysis, you remembered from that too. That's less than or equal to b minus a over 2 to the n. In this case, that's 1 minus 0 over 2 to the n. 1 over 2 to the n. I want to choose n so that this is less than epsilon. Uh-oh, epsilon. What's that? Well, it's 0.01 for this example. It's similar to kind of the scratch work you would be doing in a real analysis proof. How big should n be for this to be the case? We need to solve this inequality for n. Probably nice to take reciprocals on both sides. That inequality is equivalent to 2 to the n being bigger than 100. flipped both fractions. 1/2 to the n becomes 2 to the n. 0.01 is 1/100th. Flip it, it becomes 100. You don't even need to use logarithms to solve this. If n is a whole number, just think about it. N would have to be bigger than 7 for that to be the case. I guess greater than or equal to 7. Let's say n is greater than 8 or than 6. Let's write it that way. If n is a whole number. To find a more precise solution set of this inequality, if you allowed irrational numbers, for example, you'd want to use logarithms. N would be greater than, well, I could write a log base 2, but ln of 2 to the n would have to be greater than ln of 100. This is the same as n times ln of 2. Solve that for n. N would have to be greater than ln of 100 divided by ln of 2. That's going to be an irrational number. What is it approximately? Ln of 100 divided by ln of 2. It's about 6.64. We know n equals 7 is good enough. Oh, well, we did already. 2 to the 7th is 128. There's a more precise, again, answer to the solution set of this inequality, but n is a whole number, so we can use this. And so the minimum number of the value of n that gets within 0.01 is minimum n is 7. 7 steps will guarantee that we're within 0.01. Now, actually, 2 steps almost got us within 0.01, right? More accurate answer was close to 0.74. It was 0.739. It got almost got us within 0.01. Actually, that was, yeah. If you're thinking of this as being your first step to get 0.5, I guess you'd call it the second step to get to 0.75. Okay, so we want to think about error bounds in this class. There's our first example. Question?
Yeah, so like you had an error, let's say you said that epsilon is equal to 0.02.
Mm-hmm.
As we said, like the second one is within that bound, but if you did the method you did, you would say that 5. Is that just saying like then every number after that will be closer?
Yeah, I mean, if this were 0.02 here, then we get a 50 here. And n being greater than 5, meaning 6 or greater, would be good enough. But yeah, once you could also solve it for a more precise answer.
Because it wouldn't include the 2. Is it just saying that like after that, every number will be?
This is just giving guarantees.
Okay.
It's not saying it couldn't do better faster. Yeah, good question. Going to share some Mathematica code with you to do the bisection method faster. If you ever need to, or if you ever want to. This code actually is not my code. It was created by a previous professor here named Brian Turnquist. I'm not a computer scientist. I don't program much. I mean, I program Mathematica sometimes, but I don't really typically do while loops, for example. I could take the time to break this down, but that would be kind of time consuming and would be beyond what we're ordinarily doing. But let me just show you how to use this. This is one way to create a table that is going to estimate this root of the equation cosine of x equals x. This code then is not as general as it could because we are talking about this particular example, since you see the 0.739 in there, and that's sort of already assuming we know the answer. But it does create a table of values in kind of a nice way. So this is a nice output to look at. We've got a column for the A values, F of A values, B values, F of B values, which we don't really need for the method, but is maybe nice to look at anyway. P values, F of P, and the distance between the endpoints that you see there. And we started out here with the interval from 0 to 2 in this program. So it's not the exact same table because of that. But we do see the p-values are converging toward 0.739 And f of those p-values is getting really, really close to 0. So that's kind of nice. This is code that generates just a single output. And you might say, well, if all you're after is a single output, you might say this code is better. To use this code, what we're doing essentially is we're creating a, you might call it a subroutine. In Mathematica, you'd actually call it a function. I'm calling that function bisection. To use this, you type in your function that you want to find the root of, in this case, cosine of x minus x. And once we've entered all this code, you put the function here, you put your left endpoint here, you put your right endpoint here, and you put your error tolerance here. 0.01 is the tolerance right there. And it will spit back some output telling you your approximation to within 0.01. The first time you get within 0.01, I believe. Does that make sense? I'm a little confused by that because it should be, I would think, the 0.75. Okay, that's the 0.75 is not within 0.01. It's almost within 0.01. If I made this 0.012, we're not getting the 0.75 there either. Okay, so I'm a little confused about why that's not working. All right, maybe we should not worry about that particular code. It's not giving me what I'm expecting. I'll have to play with it and maybe get back to you about what's going on. Okay. But I will share with the code with you in after class anyway. Maybe it will need some fixing. You should also be familiar with how to think about this error bound in what's called big O notation in this class. Using big O notation, we can write the conclusion of this theorem, this error bound, in this way. Pn equals P plus big O of 2 to the negative n. Seen this in discrete math before? What we're saying is our approximation Pn to P equals P itself plus some term of order 2 to the negative n. Meaning the error term behaves like 2 to the negative n. That's the intuitive way to think about it. And that's what this error bound theorem guarantees. The absolute error is less than or equal to some constant that doesn't depend on n divided by 2 to the n, which is the same as that constant times 2 to the negative n. The constant b minus a could be big. You know, if you pick your bigger and your initial interval from a to b to be big, then b minus a will be big. But that's irrelevant. In the long run, the error goes down with the same kind of speed, you might say, as 2 to the negative n, which is exponential decay. So you could call it fast convergence, though we will talk about algorithms that are even faster.